everyone, welcome back to my Max and Additional Max channel. For today's Additional Max video teaching, I would like to share with you one of the most impressive video that I ever seen in teaching application of differentiation. As you know, the application of differentiation is actually not easy to understand and even not easy to
The farmer has 2,000 feet of fencing and wants to enclose a rectangular field that borders a straight river. He needs no fence along the river. What dimensions will maximize the enclosed area?
Lesson on application of
So first,
differentiation.
let's try to get a visual interpretation for the question here. So a farmer has 2,000 feet of fencing. So imagine this is the fencing with a length of 2,000 feet. Now the farmer wants to enclose a rectangular field. So the farmer wants to enclose a rectangular field. You see that? Wants to enclose a rectangular field. Something like this. That borders a straight river. Okay, a rectangular field that borders a straight river. So let me just draw it out. Okay, so a rectangular field that borders a straight river. Now, along the side of the river, the farmer needs no fence, right? So along the side of a river, the farmer needs no fence, assuming that the cows cannot swim and escape through the river, right? Yeah, so now, what dimensions, so what length and width, what dimensions will maximize the enclosed area? So what dimensions will maximize the enclosed area? So to get a better understanding for the question here, let's consider a few cases, okay? Now, one way to go about building this rectangular field is the farmer can build something very wide and shallow, right? So for example, so the farmer can build a rectangular field that's very wide up top. So something like this, right? See? Very wide up top and shallow on the sides, right? Yeah, so something like this. Okay, so let me just draw it out. So very wide up top and very shallow along the sides, right? So something like this. In this case, we'll get an enclosed area like this, right? Now another way to go about doing this is build something very narrow up top and very deep along the sides, right? So something like this. Very narrow, see? So very narrow up top and very deep along the sides, right? So something like this. Okay? Yeah. So see? Something like this, right? Very narrow up top and very deep along the sides. In this case, we will get an enclosed area like this. Now we can also do somewhere in between, right? So up top, not very wide, not very narrow, but somewhere in between. So more like a square then, right? So something like this. More like a square, right? Having equal length and width. Right? Yeah, so something like this. So build more or less like a square field, right? Having equal length and width, right? And in this case, we'll get an enclosed area like this, right? More like a square, okay? So the question now asks us, how should the farmer go about designing the dimensions, designing the length and width in order to have a maximum enclosed area? hopefully the farmer knows a bit of calculus so that he can figure this out easily. So farmer has 2,000 feet of fencing. So I've got 2,000 feet of fencing. So fencing with a length of 2,000 feet. Now farmer wants to build a rectangular field of 3 sides. Okay? So let's build the first side. So first, let's chop off one section. Let's chop off one section of the fencing. Okay, so let's chop off this section with a length of x feet. Okay, and we're gonna put this section right over here with a length of x feet. Okay, now let's build the second side. So now we know that for a rectangle, the opposite sides must have equal length, right? So let's build the opposite side now. Okay, so for the opposite side, let's chop another section with the exact same length. Okay, so let's chop off another section with the exact same length, x, and then put it on the opposite side of the rectangle. Okay, so also with the length of x. Now, how much fencing do we have left? Well, let's see. Total length is 2,000 feet, and we took away how many sections already? We already took away 2 sections and then put them right over here, right? So the remaining length will be 2,000 minus how many x? Minus 2x, right? So the remaining length right here will be 2,000 minus 2x, minus 2x, okay? So the remaining section right here, we're just gonna put it right over here, up top. Okay. So the last piece of the rectangle has the length of 2,000 minus 2x. Next, we gotta ask ourselves, what are we trying to maximize here? Well, in this question, we are trying to maximize the area. So that means we have to write a function for the area of the rectangular field, right? See, in this section of optimization, whatever you try to maximize or minimize, we have to write a function for that, right? So in this case, we're trying to maximize the area, so we have to write a function for the area. Okay, so let's go. So the area of a rectangle is equal to length times width, right? Yeah, so in this case, let's use A to represent area. Okay, so in this case, our length is 2,000 minus 2x, right? So our length is 2,000 minus 2x. Now what's our width? The width of this rectangular field is x, right? See, length times width. So the width is x. Okay? Now, let me just quickly expand this polynomial by multiplying the x into the bracket here. Okay, so multiply x to 2,000, we get 2,000x. And next, multiply x to the second term right here inside the bracket, negative 2x. So x times negative 2x, we get negative 2x squared. Right? So as we can see here, we now have an area function in terms of x. So this area is a function of x. Now, looking at the area function, what type of function are we dealing with here? Well, let's look for the highest exponent in the polynomial. So in this case, the highest exponent in this polynomial is to a squared. And that tells us that the area function is a quadratic function. Now, the graph of a quadratic function is a parabola. Let me ask you, in this case, do we have a parabola opening up or opening down? Look, in front of the x squared term, we have negative. So we should expect the area function to be a parabola opening negative, a parabola opening down, right? So if I draw the graph of the area function, I should expect to have something like this. An area function denoted as a of x, an area function as a function of x, right? Where x is the width of the rectangle, right? Where x is the width of the rectangle. The width of the rectangle, right? So now, if I sketch the graph for the area function, I should expect to have a parabola opening down, right? Something like this. A parabola opening down, right? Now, from the graph, we can obviously see that the maximum area occurs right here, right? Occurs right here, right? So the absolute maximum of a quadratic function is always just the local maximum, right? Yeah, so the absolute maximum, the absolutely highest point in the quadratic function always happen at the local maximum, at the vertex, right? Now, in the previous section, we talked about critical numbers. We learned that every local extreme, whether it's local maximum or local minimum, always occurred at critical points, right? So this local maximum is gonna occur at a critical point where the derivative of the function a prime of x is equal to 0, right? In other words, if you draw the tangent line to the function at this critical point, at this local maximum here, we will have a horizontal tangent line with slope equal 0, right? Yeah. So now we know that the maximum area occurs when the derivative of the area function is equal to 0. So now let's take the derivative of the area function. Okay? So the derivative of the area function a prime of x is then equal to, now to take the derivative of this polynomial, we can simply apply the power rule, right? So the derivative of the first term, 2000x, is just 2000, right? And then minus, now the derivative of the second term, 2x squared, is 4x. Now, okay? Now to locate the maximum, we have to set the derivative to be equal to 0, right? So let's set the derivative equal 0. Okay, so 0 is equal to 2000 minus 4x. So solve the equation here, we get x is equal to 500, right? So x right here is equal to 500 because 4 times 500 is 2000 and 2000 minus 2000 is equal to 0. Okay? So solving the derivative equation here, we found that the maximum occurs when x is equal to 500, right? When the width of the rectangular field is equal to 500. And guess what? When x is equal to 500, when x is equal to 500, when x right here is equal to 500, and guess what? We're done. We found the answer. See? This particular dimension will give us the maximum area right here. So we're ready to write the answer, okay? So let's write the answer. Need some space. Okay. So, the final answer. To maximize the area, the dimension must be, so our answer is, the dimension must be what? Well, the length, in this case, is defined as 2000 minus 2x, right? It's 2000 minus 2x, right? So in this case, our length must be what? 2000 minus 2x is what? X is 500, right? So let's set x to be 500, okay? So 2000 minus 2 times 500, well, 2 times 500 is equal to 1000, and 2000 minus 1000 is equal to 1000, okay? Yeah, so to maximize the area, our length of the rectangular field must be 1000 feet. 1000 feet. Okay, how about our width? So to maximize the area, our width must be, well, width was defined as what? X, right? In this case, x is equal to 500. So to maximize the area, our width must be 500 feet. Now, what's the value of the maximum area? Well, that's easy too. So the maximum area must be what? Well, area is equal to length times width, right? So to maximize the area, our length must be 1000 feet. Our length must be 1000 feet. And our width must be what? Our width must be 500 feet. Our width must be 500 feet. Okay? Now, so 1000 times 500, then we get 5 with how many zeros? 1, 2, 3, 4, 5. 5 zeros. Okay? So the maximum area is equal to 500,000 feet squared, right? Because look, 1000 feet times 500 feet, and feet times feet, we get feet squared. Okay? And that's our answer. So if the farmer knows a bit of calculus, this is actually pretty easy to figure out, right? To maximize the enclosed area, the length of the rectangular field must be 1000 feet. So it must be 1000 feet, right? So the length of the rectangular field must be 1000 feet. And then the width of the rectangular field must be 500 feet. Okay, 500 feet. Okay? That's it. Easy, right? Yeah, so calculus is very cool. So let me just quickly put down the maximum area we got here on the graph. Okay, so the maximum point on the area function has a value of 500,000. 500,000. And the maximum occurs when x is equal to 500.
Alright, thank you, sir. I'm sure my student will have a very good understanding of the concept and the skills of solving question involving application of differentiation. Till then, I shall see you all in my next video lesson. Bye bye and have a nice day.